Okay, let's get started. Oops. Let's make sure. All right, there we go. Okay, we're getting started now. Oh, I keep doing that. Hold on. We are getting started. All right, I think we're good. Chapter 5, Achieve, is available. This is another longer assignment, so I encourage you all to get started early. It's longer because we didn't have an Achieve last week, so a little bit longer than our usual ones. My office hours today, they're usually at 1, but today I need to shift them to 2. So they're 2 to 3 p.m. upstairs. This is a good time to get started on the Achieve homework. You could do it during office hours, and then I'm there to help you along with any of the questions that you have. That's all for announcements. Your assessments, I'll pass the Scantrons back at the end of class today, so just hold off on that for now. We're going to move on to Chapter 5, Part 2, which is about solutions. So, you might remember from Chapter 1 that when we have something that we call a solution, that implies we have a homogeneous mixture. So a solution is a homogeneous mixture. You cannot see specific particles in the solution, but there are at least two different elements or compounds mixed together. When you have a solution, the pure substance that is dissolved in the solution is called the solute. So if you have salt water, salt is dissolved in the water, the salt is the solute. The substance in a solution that's used to dissolve the solute is called the solvent. So in a saltwater example, water is the solvent. So we'll use this language when we talk about solutions. When we have a solution, we can measure and discuss the concentration of solutions. So solutions that have a relatively large amount of the solute, so the thing dissolved in the solvent, per volume of solvent, these are referred to as concentrated solutions. And then solutions that have relatively small amounts of solute per volume of solvent, these are referred to as dilute. So for the saltwater example, if you have lots of salt in some water, that would be a concentrated solution. If you have just a little bit of salt in the water, that would be a dilute solution. And then you may remember also from, I think this was from Chapter 1, if we have a solution that's made using water as the solvent, we call that an aqueous solution. We probably defined that in Chapter 1, and then we've been talking about aqueous solutions for a while now. So when we have a solution, it's useful to discuss its concentration. Molarity is the most common way that we discuss concentration or measure concentration in a solution. So molarity is used to describe the concentration of a solution And molarity is calculated by dividing the moles of the solute, so the thing that's dissolved, by the total volume in liters of the solution. So if we have a higher concentration, that means we have a higher value for the moles of solute per volume. So we have a higher concentration, we have a higher molarity. And this picture here shows 4 different solutions. All of these solutions have the same volume. You can see the level of the liquid is at the same point on all of these beakers. But these all have different concentrations, they have different molarities. And so we can see that through color in this picture, but through the particle representation, we can see that at any point in this solution, we have this number of solute particles. And then if we look to a little bit more dilute, we have a fewer number of solute particles per volume of solution, and then fewer and fewer number of these solute particles per volume. Okay, so let's think about this conceptually. Let's say you are waking up in the morning, you're making a cup of coffee, you accidentally add 4 teaspoons of sugar, but you usually add 2. So what can you do? Talk to the people around you for a few seconds. What can you do to make your coffee less sweet in this scenario? All right, what are some of your ideas? Let's quiet down. Go ahead. We could add coffee. Yeah, we could add unsweetened coffee. That would make the total volume of the solution of your coffee larger, but you have the same amount of sugar. Any other ideas?
You can probably put them like in 2 cups and then add more coffee so you can have like half.
Oh, yep. So same concept, but then you're not drinking more volume of coffee. Yep. So you could split the concentrated sugary coffee into 2 cups and then add more coffee to each of those cups. What about adding water? Should you add water?
Yeah.
You could add water. That would decrease the sweetness. That would make your coffee less sweet, but that would also decrease the concentration of the coffee flavor, of the caffeine. So overall, everything would be more dilute. So we could, let's just say, we'll specify that we have unsweet coffee. And that would probably be your best bet. Once the sugar is dissolved in the coffee, it's really difficult to remove the actual sugar particles. You'd have to filter it out, and I don't think you want to do that in the morning. Okay, now let's do a calculation. So we are going to calculate the molarity of a solution. We're preparing the solution by dissolving 1.2 grams of glucose, so sugar, in enough water to prepare a 525 milliliter solution. So remember, molarity is moles of solute over liter solution. So where should we start here?
Convert grams to moles.
We can convert grams to moles. Is that what you were going to say?
I was going to say convert milliliters to liters.
Or convert milliliters to liters. We could start at either point. But we need to know if we're starting with glucose, we'll convert grams to moles first. If we're starting with 1.2 grams of glucose, we need to convert that to moles of glucose. So moles of solute is 1.2 grams of glucose times its molar mass. Its molar mass is 180.16 grams per mole. And if we simplify this equation, we have in 1.2 grams, there are 0.00661 moles of glucose. Is that right? Did anyone calculate that? Yeah. So you have? Okay. Yes, so if we were ending the calculation here, it should be 2 significant figures, but we're not done with the calculation. We still need to calculate molarity, so we'll keep some extra sig figs here. So we're not rounding too early. Okay, so we have moles of the solute. Now we need liters of solution. We have 525 milliliters. Need to convert this to liters. 1 liter is 10 to the third milliliters. So we're just using our milliliter to liter conversion to make sure we have liters of solution. Now we have moles of the solute and total volume of the solution, so we can use these values to calculate molarity. So going back to that first equation, mole solute over liter of solution, I'm going to add in these values, 0.00661 moles over 0.525 liters. Just adding these arrows to show where we got those values. And then we simplify this, we get a molarity of 0.0126. Capital M for molarity is the unit for molarity, but when you're, in the next slide, we'll see an example of this. When you are using molarity as a conversion factor, so just like we've used density as a conversion factor, we can use molarity as a conversion factor. Then you'll want to include, you'll specify that the capital M represents moles per liter. Both are correct. You should be able to recognize moles per liter is the same thing as capital M. Okay. Next slide. I'll go back to this one while you're working in case you need to, in case you're still writing. But the next slide will be an iClicker question. So we're going to now use molarity as the conversion factor like I just mentioned. So you have the concentration of the solution, and your question is how many moles of the solute are present in 2 liters of that solution. So I'll get this started and I'll go back to this in case you need it. Say 1 more minute. Let me know if you're stuck.
I know somebody that had like they had like 7 dogs. Or like I walked into their house and like this red dog was jumping at my feet. They're all pups. Yes, I pulled into like the valley. I can't even see my shirt anymore. It's just like hairy dog.
All right, let's get your answers submitted. Give you a few more seconds. All right, I'm gonna end it here. Let's see what we're thinking. Okay, I saw the same mix in my earlier section. So we have a 0.85 molar solution. So that's 0.85 moles per liter. And we have a 2-liter sample of that solution. So if we have 2.0 liters of a solution that has 0.85 moles per 1 liter, we use the molarity as a conversion. So now we're doing 2 times 0.85, and this gives you 1.7 moles of solute. We've canceled out units of liters, so we're left with moles there. Questions on this or the last slide? Okay, well, we're going to move on then to the concept of dilution. So we said if we have a dilute sample, it has relatively few moles of solute per volume. We can take a concentrated solution and dilute it by adding more solvent. So dilution is the process of adding more solvent to decrease the concentration of solute in a solution. Now, if we have, let's go back to the coffee example. You have 4 teaspoons of sugar in that coffee. If you add more unsweetened coffee to your mug, you still have 4 teaspoons of sugar in that sample. So the total number of solute, in that example, sugar is the solute, that's what's getting dissolved in the solution. The total number of solute molecules stays the same. But we're adding more solvent, so we're increasing the volume. The total volume increases. since we have the same number of solute particles in a larger volume, that means the concentration decreases. So we have two images here that show dilution. We start with these test tube samples. We have, you can see both by the color, we have a darker color here. And that's because we have a higher concentration of solute particles per solvent, per amount of volume. And this particle picture here is showing the water molecules, which are the red and white molecules, and the solute particles dissolved within the water molecules. Well, if we add water, so solvent here is water, if we add water to the solution, we now have a more dilute solution. There, in a area, there are fewer solute particles because there's more water present. So the solute particles are spread apart. That picture at the top is showing the same thing. So we have a beaker with a certain number of solute particles. Solute particles are represented by those circles. If we add solvent, we have the same number of solvent particles, but lower concentration. So fewer number per volume. If you were to take, if we look at this example here, if you were to take 1 milliliter of this solution and 1 milliliter of this solution, the more concentrated solution will have a higher number of the solute particles because it is higher concentration. So let's do this question here. Looking at the 4 different options, which of these, this will be an iClicker. Quick one here. Which of these represents dilution? Say 20 more seconds. I think there are a few of you that still need to respond. All right, ending it here. All right, a little bit of a mix. So nobody picked A. Why isn't A dilution? Yeah, we added more solute. There's the same number of solvents. So actually what's happening in A is that we're getting more concentrated. What about, let's go to C. What's happening in C? Someone that didn't pick C, will you explain why this is not dilution? We poured half of it out, yeah. So we have about half the volume and half the number of solute particles. So the concentration, if we assume the volume is half, then we have the same concentration. Decrease the solute particles by 1/2, and we decrease the solvent by 1/2. Now, what about B and D? How about, before you say it out loud, talk to the people around you about, so D is dilution, but B is not. So explain to the people around you why B is not dilution, but D is. Okay, someone on this side, why is B not dilution? The amount of solute increases. Yeah. Okay, we've increased the volume, we've increased the amount of solvent, but we've also increased the amount of solute particles. So we cannot say if this is dilution or not, because we have both more solvent and more solute particles. Why is D dilution?
The amount of solvent.
The amount of solute stays the same. Yeah. So the amount of solute stays the same, 6 particles here, 6 particles here, but we've increased the volume, so we've added solvent to increase the volume. So volume increased, number of solute particles did not. So D is our dilution. Okay, so that's kind of the visual of what's happening when we dilute something. Now we're going to go into the math of calculating dilutions, concentrations of dilute samples. So our question here is what concentration will result when 0.75 liters of a 1.6 molar solution is diluted to make a 3-liter solution. So we're taking 0.75 liters, less than 1 liter of a solution that has sodium chloride dissolved in it, and then adding water to get a total volume of 3 liters. We want to know what that ending molarity is, that ending concentration. It's getting diluted, we're adding more solvent, so the molarity should be lower, but we want to actually calculate what that value is. So anytime you're diluting something by just adding more solvent, just like that coffee example, where the amount of sugar stays the same, the amount of your solute is going to stay the same. So you can calculate the moles of solute by using that solution where you already know the molarity. So we're taking 0.750 liters of the 1.6 molar solution. That's the solution that has the solute. We can determine how many moles of that solute are going to be present in our final solution. So we can take 0.750 liters times concentration of that solution, so 1.60 moles of sodium chloride per 1 liter. So 0.750 liters of a 1.6 molar solution is 1.20 moles of sodium chloride. So if we're taking 0.750 liters of a solution with a known molarity of 1.6 molar, in the 0.750 liters, there are 1.20 moles of sodium chloride. That's also the amount of sodium chloride that will be in our diluted solution, because we're not adding any more sodium chloride or taking any away. So we can find now the molarity of the diluted solution by taking the moles of sodium chloride, so that's our moles of solute, divided by total volume. The rest of the solution is water. So molarity is 1.20 moles divided by 3.00 liters. So total volume is 3.00 liters, and this is our moles of solute, 1.20 moles. So the molarity of this solution is 0.400 molar sodium chloride solution. So in this example, we've taken a volume of the solution, 0.750, that concentrated solution, and diluted it by a factor of 4. We've quadrupled the volume from 0.75 to 3 liters. If we dilute something by quadrupling the volume, then the concentration will be diluted by the same factor, so by a factor of 4. And we see that if we compare the concentrations, we start with 1.6 molar, you see that at the top, and then 0.4 molar. And we'll see this pattern. If you dilute something by doubling the volume, then the concentration decreases by a factor of 2 as well. So everything that we've covered on this slide is used to generate the equation that we have on the next slide. So if we're diluting something, this calculation can only be used for dilutions. But if you're diluting something, we said this on the last slide, the number of moles of the solute does not change. So total moles of solute in the concentrated solution is equal to the total moles of solute in the diluted solution. That's what we calculated, moles of sodium chloride in the 1.60 molar, same number of sodium chloride in the diluted solution. So that is true. We can also say that before the dilution, the molarity of that solution times the volume of the solution that you're using for the dilution will equal the moles of the solute. So moles or molarity times volume, which is what we're showing here, M1 times V1, is equal to moles per liter. So those are the units of molarity, times liter for volume, so that gives you moles. So if you take the molarity of something, multiply it by its volume, you get moles of solute. And that's true for your concentrated solution and your diluted solution. For any solution, you can calculate moles of solute by taking molarity times whatever volume you have of that solution. So since initial molarity times initial volume gives you moles of solute, and final molarity times final volume gives you moles of solute, and the moles of solute of the dilute solution are equal to the moles of solute of the concentrated solution, then we can generate this final equation where the initial molarity times the volume that you take of that concentrated solution is equal to, so multiplying those together, is equal to the molarity of the diluted solution times the volume of the diluted solution. Yeah.
Isn't there an equation like that, but with moles instead of molarity?
There is, yeah. But it's not in this chapter. I don't know if we'll get to it this semester. So anytime you're doing a dilution, and only when you're doing a dilution, you can use this equation to solve for any of the unknowns. As long as you have 3 values, you can solve for the last. So let's do an example here. A learning check. This one's not an iClicker. We've got this long word question. We're going to read it and then determine what information we have and what we need to do to solve the problem, answer the question. So an agricultural chemist wished to study the effect of varying fertilizer applications on the growth of tomato plants. So a little bit of background. The chemist prepared a stock aqueous solution of urea. The formula of urea is provided there, NH2,2CO, by dissolving 3.5 grams of this compound in enough water to make a 2-liter solution. So they make this stock solution, and then they dilute that stock solution to get varying concentrations in one. So it says she prepared a series of more dilute solutions to apply to her tomato plants. One of these solutions contained 5 milliliters of stock solution diluted to give a final volume of 25 milliliters. We're asked to find the concentration of urea in the diluted solution. So lots of information here. Let's start with what a stock solution is. The question kind of implies it, but a stock solution, that is when we're purchasing solutions for a chemistry lab, we purchase a stock solution. So many solutions are provided at a certain concentration. So if you have an acid, it's not pure acid, it'll be acid dissolved in water at a certain concentration, like 1 molar HCl, hydrogen chloride, or hydrochloric acid. Or same thing for a base or other solutions. If you look at a bottle in your lab, if you're able to see a bottle, it'll have a concentration on that bottle. The concentration that you purchase is not always the concentration that will be used in an experiment, or in this case, used to test on tomato plants. And so we take the stock solution and dilute it to whatever is required for an experiment or for whatever procedure is needed. So the stock solution is what we're starting off with, and then in this case, we're going to dilute the stock solution. So we need to find the molarity of the stock solution, which is the information required to find the molarity is the grams, the amount of urea that's dissolved to make that stock solution, and 2 liters. So we can calculate molarity of the stock solution there, and then we can do our dilution M1V1 equals M2V2 to find the molarity of that diluted solution. So we're given grams of urea. We're trying to find concentration. We need to convert to moles. So let's convert to moles, and then we'll calculate molarity. So 3.50 grams of urea, NH2 to CO. We can convert to moles using its molar mass. Its molar mass is 60.061 grams per mole. So 3.5 grams of urea is 0.05827 moles urea. So to make the stock solution, the chemist measured 3.5 grams, which is equal to 0.05827 moles. 0.05827 moles were added to 2 liters of solution of water. So now we can calculate molarity. This is our stock solution, so we're going to label this as M1. This is what we're diluting. M1 is the moles of urea divided by total volume, which is 2.00 liters. So M1 is 0.02914 molar. Okay, so that's our molarity of the stock solution. So she takes the stock solution and dilutes it by taking 5 milliliters of the stock solution and adding water to it. So our volume of the stock solution is 5 milliliters, which we need to convert to liters. So this is the volume of the stock solution that's used for dilution. So we have M1 and V1. We're looking for M2, the molarity of the diluted solution. So we don't know what that is. We will calculate that using M1 V1 equals M2 V2. And then V2 is that final volume, 25 milliliters. So we just need to convert that to liters. So this is volume after dilution. So we've got M1, V1, and V2. We use our M1, V1 equals M2, V2 to solve for M2. So now we're just plugging in values. M1 is 0.02914 molar. V1 is 0.005 liters. I'm leaving off sig figs just to save room, but when you're going through, you might include all the sig figs so you don't lose track, or look back here to determine sig figs. And then this is equal to M2 times our final volume, 0.025 liters. Again, I left off a couple of sig figs there. If we solve for M2, we should get 0.00583 molar. Questions on this problem here? Okay, I'll leave it up. I'm going to pass back your Scantrons. A couple of notes. The score on the Scantron is the number that you got correct out of 30. So your score in Blackboard is that your score on the Scantron multiplied by 2 because the exams are out of 60. So each question is worth 2 points. On Blackboard, I haven't your scores are hidden. So they're all hidden from you right now. I will unhide them after class. And then what I did on Blackboard is I also added in any extra credit. I divided the extra credit between your first 2 exams to give you, on average, higher score. So if you had, for example, if your unit exam 1 score was 41 and your midterm was 43 out of 60, and you got 4 extra credit points, you completed all of the learning curves, then I would have added 3 to your first exam, so you'd get 44, and then 1 to your midterm, so you have a 44 on both. So you can check that when everything's available on Blackboard. You're just getting the Scantron, so the actual packet and key will be posted on Blackboard later today. You can compare everything to the key. I think that's all. Oh, one more thing. If your grade in the class is lower than a C, let's schedule a meeting so that we can talk about what to do to ensure that you are passing the class. A C is required to enroll in 1080 in the winter semester. So if you get lower than a C, you can't enroll in 1080. So if your grade currently is lower than a C, send me an email so we can meet. Good job. Yeah. Helium. Amira? Muhammad H. Omar? Yeah.
Well, I know, I'm sure, this is literally the last good night. Yeah, well,
Everyone have their
Wait, your office hours are at 2 today?
2.
Okay, I'll be there.
Okay. See you there.